Today we're going to solve a bunch of constant acceleration kinematics problems, but we're also going to look at some strategies, both psychological and mathematical strategies that you can use to help you solve these problems.
Shortly, I'm going to write down 4 equations that are going to help us to solve kinematics problems. But they only apply under certain circumstances. The first thing is that we must have uniform acceleration. The acceleration can't be changing. The other thing is these equations are really going to be vector equations, but the motion is going to be confined to a one-dimensional situation. That means we can have objects moving, say, left or right, or up or down, etc. And in a left-right system, anything to the right, of course, is positive, and anything to the left is negative. So we can talk about, say, positive displacements. We could talk about, say, negative velocities if something's moving to the left, and we could also talk about positive or negative accelerations. If something is being forced or pushed to the right, it would have a positive acceleration. So these are vector equations, but the vectors are represented as plus or minus signs. We usually don't put all the vector signs in simply because it's a lot of extra work. So we'll usually write things like VF equals VI plus AT. And we usually don't put the vector sign in there, but it really is there. We're just a bit lazy in writing that out. But once again, in a one-dimensional situation, the vector nature just represented by a plus or minus sign. As I said, we have 4 equations for one-dimensional uniform acceleration. Now, if you look in some textbooks, you're going to get 5 equations there. Other textbooks will give you 3 equations. And the reason you can get more or less is because some of them can be derived from the others. So the first equation is that the final velocity will equal the initial velocity plus the acceleration times time. And I like to give each of these equations a name. I like to call this the how fast equation because it's going to tell me the speed and velocity as a function of time. Now the second equation is that the displacement will equal the sum of the initial and final velocities divided by 2, which is really going to be the average velocity multiplied by time. And I like to call this the how far equation. Well, it's really displacement, but in many circumstances it'll tell me how far the object has traveled. But it's using an average velocity. So I call it how far average. Third equation, I call this one how far acceleration. Once again, it tells me how far, it tells me the displacement. You're using the acceleration in this equation, whereas this equation uses the average velocity. Third equation, final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. I like to call that the no time equation, and that's because time does not appear in this equation. And that's going to lead to an important strategy later on. Something else to note here is that if you're using different websites and different textbooks, you're going to see different symbols being used. Let me just mention a few of the common ones. If you're talking about initial velocity, well, I'm using a VI. The IB uses a U, and a lot of textbooks will use a V naught. For final velocity, of course, I'm using a VF, but a lot of textbooks just use a V, and the IB will just use a V. And then for displacement, I'm using a delta X. The IB likes to use an S. So be aware of that. It's not for speed, it's for displacement. And a lot of, especially Canadian textbooks, like to use a delta D for displacement. What we're going to do is very briefly show the proofs of these 4 equations. The first equation simply comes by rearranging the definition of acceleration. And acceleration is the rate of change of velocity. That is, A is equal to Vf minus Vi over t. Now, if I multiply both sides of that equation by t, I get that At equals Vf minus Vi. And then what I'll do is add Vi to both sides of the equation, so I'll get At plus Vi equals Vf, and then rearranging that so that I've got Vf on the left-hand side, I get Vf equals Vi plus At. And this equation should make a lot of sense to you. Let's say your initial velocity is, say, 10 meters per second. And let's say you're gaining speed at 2 meters per second every second. And you do that for 3 seconds. Well, that means that due to that acceleration, you should add another 6 meters per second to your original speed to get 16 meters per second. So this should be a very physically intuitive equation for you. Our second equation just comes from our definition of average velocity. Remember that velocity is equal to the rate of change of displacement per unit time. For an average velocity, under the situations where you have uniform acceleration, and that's very important. When you have uniform acceleration, that means your velocity is growing at a constant rate. And that means your average velocity is going to be exactly halfway in between your initial and your final velocity. So to find the number that's halfway in between VI and VF, we just add VI and VF and divide by 2. So it's kind of like when you get 70 on one test, you get 80 on the next test, your average would be 70 plus 80 divided by 2. So now what we want to do is rearrange for this delta x here, and when we do that, we get equation 2. Now, if we want to derive equation 3, what we do is we take equation 1, VF equals VI plus AT, and we're going to substitute it into equation 2. So where I see VI plus AT, I'm going to use that and substitute it in for VF right here. And if I do that, I'm going to get that delta x is equal to VI plus AT all over 2 times t. So I'll get 2VI over 2 plus AT all over 2 all times t, which gives me VIT plus 1/2 AT squared equal to the displacement. So there's equation 3. Now for equation 4, what we do is we take equation 1 and rearrange it for time. So equation 1 was VF equals VI plus AT. If we rearrange that for time, we get that time is equal to VF minus VI all over A. Now we're going to take this quantity here and substitute it into equation 2. Equation 2 was delta x equals VI plus VF all over 2 times t. So what I want to do is take this and replace this t here. So what I'm going to get is VI plus VF all over 2 times VF minus VI all over A. Multiply the denominators, I'll get 2A, and then in the numerator I'll get VI, VF minus VI squared plus VF squared minus VF, VI. Of course the VF, VI terms go out, so we get VF squared minus VI squared all over 2A equal to delta x. Multiply both sides by 2A, I'll get 2A delta x equal to VF squared minus VI squared. Then I'm going to add VI squared to both sides. I'll bring that around here. So I'll get that VF squared is going to equal VI squared plus 2A delta x. And that's the fourth equation. These 4 equations allow us to do all kinds of problem solving in physics, and it's our first real exposure to physics problem solving. But it's something we're going to do over and over again in this physics course. Many people get absolutely addicted to physics problem solving. They just love that challenge. And there's certain mental attributes and strategies and understandings that I think people that are good at physics problem solving seem to have. Now, in terms of mental attributes, the first thing is something that you need in anything that you want to do well, and that is you need to believe in yourself. Because if you don't believe in yourself, you're not going to have enough persistence to overcome the obstacles in problem solving. So you have to also be somebody who is very persistent. At the same time, you need to be flexible, because often you need to change your strategy. You need to kind of expand outwards in order to solve the problem. So you also have to be flexible. And the other thing is something I call listening to the glitch. And what I mean by that is often when we're solving problems, we'll get a subtle sense that something's wrong. And somebody who's a good problem solver listens to that. They realize that they're doing something wrong, and they listen to that and they try to figure out what it is that's going wrong. So I think self-awareness is very important when you're solving problems in physics. Now, on a more practical note, sorting strategies, number one sorting strategy is make a diagram. Because what you're really doing when you make a diagram is you're taking all those complicated words and sentences and you're boiling it down to what's really essential. Just a few numbers and what they mean. I would encourage you on any physics problem solving to do some sort of little diagram just to organize the meaning of the numbers given in the problem. And the other big sorting strategy is going to be called making a variable list. And we're going to do a lot of that in this video here. Very useful technique, and they work alongside the diagrams very effectively to help you solve relatively simple problems. And the other thing that I always notice about people that are good at physics, they're always grounded in the physics principles. They're not just solving abstract mathematical equations. They understand the physics. And then what they do with the equations is the equations to them, it just represents a guide to the physics. A person who's good at physics problem solving will always try to understand an equation in terms of the physics involved. Now, I said earlier in the video that we'd be doing a lot of variable list in this video. Let me show you how a variable list works. We've got these 4 kinematics equations, 1, 2, 3, and 4. Now, if I look at any one of these equations, here, first equation, well, we have a delta x in that equation. We have a vi, we have a vf, and we have a delta t. But we don't have an acceleration in that equation. And if we look at the second equation, we've got a vi, we've got a vf, we've got an a, and we've got a delta t, but we don't have a delta x. Third equation, this time we do have a delta x, we do have a delta t, we do have an a, we have a vi, but we don't have a vf. And then this last equation, remember I called it the no time equation, well, of course it has no time in it. It does have vi, vf, a, and displacement. So what we do with a variable list is simply to list those 5 possible variables. We have vi, vf, a, t, and delta x. So let's say we've read through the problem, we've made our diagram, and let's suppose that we know vi is 0, vf is, say, 20 meters per second. We're being asked for delta x, and we know the acceleration is 3 meters per second every second. So what you want to notice here is that all the variables except t are being used in the problem. 3 of them are given, 1 of them we're being asked for, and 1 of them is not involved. So then we come over here and we notice that our 4th equation is the one that doesn't involve time. So that would be the equation that we'd use, because this would be a situation where no time is involved. So what I'm going to start with is a few questions where we don't need a variable list. I'd prefer that you rely on your physical reasoning skills. I want you to practice this skill of using the equations as guides to understanding the physics. What I'd like you to do is to pause the video, read the question over, try it out for yourself, come back for the answer. It's always a good idea to start off with some sort of diagram. So we've got a ball on a ramp, and we're giving it a speed of 10 meters per second. However, there's going to be an acceleration, and we're told the acceleration is 2. Now, make sure you realize the acceleration has to be opposite to that initial velocity up the ramp. So it's going to be a negative 2 meters per second squared. So this was really just a magnitude that they were giving us, and we had to choose the direction. Hopefully in A part I, what you said was, well, it was moving at 10 meters per second, and then it loses 2 meters per second of speed every second. That's what that acceleration means. So it loses 2 meters per second every second of speed. So it was going 10 meters per second. It should lose 2 meters per second of speed in 1 second and be going at 8 meters per second. In part 2, well, it started with a speed of 10 meters per second, but then it lost 2 meters per second of speed every second, and it did that for 5 seconds. So its speed is going to be 0 meters per second. And hopefully that makes you think about what's 0 meters per second. What does that physically mean? It simply means that's the point where the object turns around. So the object has to turn around at 5 seconds. And then in part 3, we can do the same thing. It was going at 10 meters per second. We should subtract 2 meters per second of speed every second for a full 7 seconds. And you'll notice now you're going to get an answer of -4 meters per second. And that simply means that it is now heading down the ramp. Now, if we'd done this with the equation, we would have said Vf equals Vi plus At. But I'm very happy if you don't use an equation on this one, and you simply use your understanding of what acceleration and velocity are. Let's try part B. Now, in part B, you're asked for displacement. You're asked for how far. So you're probably going to use the how far equation. And because we know the acceleration, we're probably going to use the how far with acceleration equation, which would be VIT plus 1/2 AT squared. But let's think a little bit about what this means. The object was going upwards at 10 meters per second, and in part I did that for 1 second. In other words, it would have gone up 10 meters if there was no gravity. But of course, gravity has an effect, and so we're going to have to subtract off 1/2 the acceleration times the time squared. So we're going to get 1 meter here, and that would be due to gravity. So the net result is it's going to end up 9 meters up the ramp from where it started. And then we do this exactly the same in parts 2 and 3. Let's quickly solve for those. We would have 10 times 5 minus 1/2 times 2 times 5 squared. We're going to get 50 minus 25, and that'll give us 25 meters. Right? And after 5 seconds, that's the turnaround point. This is at turnaround. So that's the maximum distance that the object's going to go up the ramp. And then in part 3, once again, we would go delta x equals 10 times 7 this time, minus 1/2 of 2 times 7 squared, and we're going to get 70 minus 49, or 21 meters. So it's a positive 21 meters. That means it's ahead of the starting point. So it's going to be kind of a situation like this. Say the ball was pushed from this point. It's going to go up by 25 meters. That will take 5 seconds. And then it's going to fall back down. And this distance here would be 21 meters. And that would be at 7 seconds. So it takes 5 minutes going up and 2 seconds coming down. Which means we're now ready to answer part C here, where we're asked how far the ball traveled after 7 seconds. So this is the distance traveled. And in part C, that means it went 25 meters up, plus another, this must be 4 meters, so that 4 meters plus 21 adds up to 25. So we're going to get 25 plus 4 equals 29 meters of distance traveled by the ball in 7 seconds. Here's an IB question from several syllabuses ago. What I'd like you to do is to pause the video, read the question over, try it out for yourself. Okay, so hopefully you said the correct answer would be B. And the reason for that is if we've got two bodies here, and let's give them both the same speed, same, then of course the distance between them is going to stay the same. But if these two objects are accelerating, then of course the one that's been accelerating for more time is going to have more speed. And the one that's been accelerating for less time will have less speed. And that means that the gap here is going to increase. Okay, another IB question. Once again, pause the video, read it over, try it out for yourself, come back for the answer. So hopefully you said the correct answer is B. That would be 8.0 seconds. And the reason for that, without using any equations, is that the acceleration is 3 meters per second every second. That means it's gaining 3 meters per second of speed every second. And how many seconds would you have to do that for in order to get a speed gain of 24 meters per second? And of course it would be 8 seconds. Another very old IB question. What I'd like you to do is pause the video, read the question over, try it out for yourself, come back for the answer. So hopefully you said the correct answer is C. I'm going to do this a little bit in reverse. I'm going to try to use some physical reasoning, and then I'll refer back to what equation I could have used. So the first thing we're going to try to find out is how much time does it take for the car to come to a stop. We've got this car moving along at 20 meters per second, and it's going to end up going at 0 meters per second. We'd like to know how much time it takes in here. So, well, it was going at 20 meters per second, and then it's going to lose 4 meters per second of speed every second. So for how many seconds would it have to do that to end up with a speed of 0? Well, of course, it's got to be 5 seconds. Now, the equation that you would use is simply that Vf equals Vi plus At. Substitute into that, and you'll get t equals 5 seconds to come to a stop. Now that we know the amount of time, we can figure out what this stopping distance is. And a very simple way to do that is to say, well, the stopping distance is just going to equal the average speed times time. And because we have constant acceleration, that average speed has to be exactly halfway in between 20 and 0. What number do you know that's halfway in between 20 and 0? Of course, it's 10 meters per second. So if you go at that average speed of 10 meters per second for 5 seconds, you're going to go a total distance of 50 meters, and that means the correct answer here is C. Here's another example, and it's one where I think a diagram is highly beneficial. So what I'd like you to do is pause the video, read the question over, make a diagram, try to answer the question, and then come back for the answer. So let's start with our diagram. There's car 1, there's car 2, and we know there's 40 meters of distance between them. Front car is traveling a little slower at 25 meters per second. Back car traveling a little faster at 30 meters per second. And we know that first car is going to come to a stop over here somewhere where it will be going at 0 meters per second because it's accelerating to the left at 2 meters per second every second. So the first thing that we're going to be asked for is the stopping distance, d here. We're then going to be asked for the acceleration of this second car, so I'm going to call that a2. And then we're going to be asked for the amount of time it takes for that second car to come to a stop. Once we draw the diagram, there's a few simple things that we can see quite easily. First thing is, for that first car, we know its initial and final speed. And that means we know its average speed. We're just looking for a number halfway between 25 and 0. That'll be the average speed as long as we've got constant acceleration. So the average speed is going to be 12.5 meters per second. The second thing that we know is that if we kind of put in a d2 here for the stopping distance of the second car, that d2, looking at the diagram, is just going to be equal to 40 plus d. And probably the third thing that we can say is we know the amount of time it takes for the first car to stop, because it was going at 25 meters per second and it loses 2 every second. So how many seconds until it would be down to 0? Well, just 25 over 2. So the time here is going to have to equal 25 meters per second divided by 2 meters per second every second for 12.5 seconds. Now that we kind of have those preliminary calculations out of the way, and I think the diagram really helped us to see that clearly. The other thing that the diagram does is it takes all those essential bits of information out of the word problem and puts them into a very compact form. So part A, what we're asked for is that stopping distance d. Well, d has to equal the average speed times the amount of time. In other words, this car is moving at an average speed of 12.5 meters per second, and it does it for 12.5 seconds until it comes to a stop. So 12.5 meters per second times 12.5 seconds gives 156 meters, as the stopping distance in part A. Part B, we're looking for the acceleration of the second car. That's the A2. Well, let's try a variable list. VI, initial speed was 30 meters per second. VF was 0. It comes to a stop. The amount of time, I'll call that T2. And the delta x is just going to be 40 plus d, but we now know d. 40 plus 156 equals 196 meters. So we know delta x, we know vi, we know vf, and we're asked for a. And so that means that we're kind of leaving time out of the equation. So we're going to want to use our no time equation. We're going to say vf squared equals vi squared plus 2a delta x. So we've got 0, 30 squared plus 2 times the acceleration that we're trying to find out, and 196 for delta x. If you work that out, you should get an acceleration here of negative 2.3 meters per second every second, or meters per second squared. So let's go on to part C. Part C, you're just looking for the amount of stopping time, the T2 here. Different ways of doing this, but I find an easy way of doing it will be to say that D2 must be equal to V average 2 times T. D2, that's the 196 meters. V average, well, that's going to be halfway between 30 and 0. Its average speed would be 15 meters per second. And the amount of time to stop, that's what we're looking for. That's the T2. Work that out, and you should get 13.1 seconds. So it's going to take 13.1 seconds for the second car to come to a stop. It, of course, comes to a stop a little after the first car does.
I chose this question because it has 3 distinct regions to it. And when I say a distinct region, I mean a place where there's a distinct acceleration. So in that first region, we have an acceleration that's positive 5 meters per second squared. In the second region, the velocity is constant, so the acceleration is 0. And then in the third region, our acceleration is negative. We don't know what value it is. And if you're solving a problem like this using variable list, you need a new variable list every time you change regions, every time you change accelerations. So pause the video, try the question, come back for the answer. So we said there was 3 regions. The first one had a positive acceleration. It was speeding up, gaining 5 meters per second of speed every second. In region 2, it was a constant speed, a equals to 0. And in region 3, we had slowing down, so we had a negative acceleration, but we didn't know what the value was. So let's do a variable list for region 1. We know it started from rest, and we want to find out, that's what we're asked for, the final speed. We know that the distance it moved across the region was 0.8 meters. And you'll notice here that time is not involved in the problem. Therefore, we can use the no time equation. Vf squared equals Vi squared plus 2a delta x. Vi was 0 plus 2 times 5 times 0.8. So Vf must equal the square root of 8.0, which would be 2.83 meters per second. I'll leave that extra decimal place for follow through. The answer to 2 significant figures would, of course, be 2.8 meters per second. And this would be your answer to part A. In part B, we have a constant acceleration. That means that Vi must equal Vf, and it must equal whatever speed we ended up with at the end of region 1. So this has to all equal 2.83 meters per second. And you'll notice here, whenever you've got a constant speed, you're really back to grade 7 physics, right? It's just speed equals distance over time, or distance equals speed times time. So we know the time here was 4.0 seconds. So the distance moved, the delta x, must equal speed times time, or 2.83 meters moved across every second for 4 seconds, giving a grand total distance there of 11.32 meters, or 11 meters to two significant figures. In region 3, our initial speed must be whatever speed we had at the end of the last region, which would be that 2.83 meters per second again. The final speed, well, it comes to rest, it comes to a stop, so the final speed is going to be 0. We know also that it spends 2.5 seconds in that region, and eventually we're going to have to figure out the distance moved, but initially they just ask us for the acceleration. So the motion equation where delta x is not involved, it really just amounts to the definition of acceleration, which is v final minus v initial all over t. 0 minus 2.83 divided by 2.5 gives an acceleration that is negative and equal to 1.132 meters per second squared, or to two significant digits, negative 1.1 meter per second squared. So that's the answer to part C. This was your answer to part B. And in part D, you're asked to find the total displacement, which is just going to be the sum of the three displacements in each region. So there's delta x in the first region. There's the displacement in the second region. And in the third region, we still need to find that out, but it is simply going to be equal to the average speed. Average speed would be halfway in between 2.83 and 0, which would be 2.83 over 2. So V average here would be equal to 1.415 meters per second. So if we moved at 1.415 meters every second and did so for 2.5 seconds, we would move 3.54 meters. So we can add that on, 3.54, add them up, and we should get 15.7 meters, or to two significant digits, it would be 16 meters total distance moved across.
Okay, so let's very briefly summarize what happened in the video. We first of all derived these four equations here as I've taken them out of the data booklet. Notice that if you're writing your exam in May 2015, this equation will not be there. And the reason it's not there is because it's a rearrangement of acceleration, and the IB were expecting that you knew the definition of acceleration and therefore could rearrange that yourself. These other three will be there. Notice that they use a U for initial velocity and an S for displacement. So some key things to problem solving. One is you've got to believe in yourself. Secondly, listen to the glitch. Be self-aware. You've always got to sort out your word problem, figure out what's really essential. Key ways of doing that are with diagrams and with variable lists. And remember, for every region of constant acceleration, you'll need a new variable list. And then thirdly, you've got to know your physics. Make sure that you're representing the physics. So don't get things reversed. In a physics course, physics is more fundamental, and you express these ideas with mathematics. So don't get over-reliant on algebra. Make sure you know the underlying physics.
So please take the time to like videos, to make comments, to ask questions, become a subscriber, sign up for notifications, become a member or a Patreon.
And that's all for today, folks. Thank you very much.